The IME 144 class at Cal Poly is changed from a manual machining process to an automated machining process. As part of this, new fixtures are needed for the family of parts that will be used to demonstrate these machines. As part of this project, we will use SolidWorks and HSMWorks and learn how to create a fixture in those and machine that fixture, as well as design toolpaths for the parts we'll be creating for the IME 144 class. This involves making the toolpaths such that they won't hit other parts and that they won't hit the fixture, and designing a fixture that will actually hold the part against the force of the tool. Lacking any inspiration, Kuba went to Yosemite, where the views inspired him to come up with a fixture using a unique Mighty Bite clamp that we were the only group to use. So between the view and a helpful chipmunk.
Hi, Chipmunk.
In the end, we want to create an easy to use, easy to understand, good looking part that will be easy to work with and easy to replace different parts if they become worn out or mistakes in machining lead to the destruction of them. Our fixture plate, as shown here with the completed assembly, shows all 6 parts in the final stage of machining. You can see the top part for op 1 and 2, the middle part op 1 and 2, and the bottom part op 1 and 2. The bottom parts are both affixed using the Mighty Bite cam clamp, and the middle and top parts are both clamped using the bidirectional Uniforce clamp from Mighty Bite. All of the parts are located primarily on the A datum, which is the flat surface of the plate. Secondarily, they're located up against Mighty Bite rails here, and the tertiary location is through pins. The pins are on the long side because in the op 1, the saw cut face is that longer side. Locating the saw cut face on the pin, so the rail or the primary datum, allows for a more accurate machining. Additionally, there's text indicating to the operator which fixture position is for which operation. Finally, there are 2 holes that allow for the clamping to T-slots and an indicating band that's recessed in order
Our main constraint was the materials we were given, so we were given a plate which was a fixed size and we had to fit all of the pieces on that size, and additionally we were only given a few different Mighty Bite fixture tools which you could use. So we were given clamps and rails, and we personally were able to use a Uniforce clamp, but not all groups were able to use that. So that's it.
Filming.
So to fit everything on the fixture plate, the first thing I did was just draw a sketch in SolidWorks of the size of the fixture plate, and then I tried to position all of the pieces within that. So here, if you can give me the camera, I had this sketch right here, and I was just manipulating everything to fit everything on. So that was my main methodology when it comes to kind of fitting into the requirements. The main thing that kind of was a breakthrough in our design was using these Uniforce clamps right here. Thanks to that, we were able to position everything onto the plate. Now, the big design constraint also that we had to deal with was the fact that this right here is the A datum, and everything has to be pushed against that. So it's kind of the short side that has to be pushed against a rail. So that was kind of the main design constraint.
that the part needs to be clamped, but not on a saw cut edge. So we weren't able to clamp it on one of the 2 edges that are the longest, making this a lot harder of a challenge. So in general, parts are located using a 3-2-1 system, where one face has 3 points locating it, another face has 2 points locating it, and the third face has 1 point locating it. In our fixture, all of our parts sit on the 3 dots that are on the bottom part of the part, and they slide up against a rail on the short end of the part, noted by the 2 triangles. The final face, noted by a square, is the saw cut edge, which is the least critical in locating and also the least accurate due to the saw cut. The tangential force, or the force of the tool on the work, was found using the ultimate strength, the area of the chip, the number of inserts, the machinability factor, and the tool wear factor. You can see our design here in the exploded cube. The first component, the main one, is the bottom floor. Then shown are the 6 parts. These aren't part of our design, however, showing them in the extended view and isometric views gives a good idea of where they're located. Next is the clamps. There are the 2 Uniforce clamps and the 2 cam clamps. Finally are the rails. One here and the others up on top, along with the pins that will locate the third datum, as well as locate the rail. This is the main technical drawing for our project. The first thing to note is the datums. The first datum, D, is the bottom of the plate. The bottom of the plate is what interfaces with the machine, and the machine is parallel, so D is parallel with the machine, and if everything else is based on D, it'll be parallel with the machine. The second datum to note is datum C. Datum C is the indicating band where the machinist will be lining up the fixture plate with the machine, so it's critical that that is what everything is dimensioned off of. The third datum is datum A. Datum A is the side of the plate, and that's what a lot of things are lined up, are measured off of in that direction. The reason why there's the datum structure is set up this way is initially I had datums for each of the individual parts. This was unnecessary, so I just slimmed it down to datums for the fixture itself and not datums for the individual parts. The datums aren't on the center lines because I felt that lining up the datums on the side and the very bottom were more accurate to the machine. So, getting into the various geometric tolerances, the first one you can see here is perpendicularity and profile tolerance for all of the various slots. Now, the perpendicularity is the most critical part here because they have to be perpendicular with C, which is the indicating band that the machinist is locating. So all of these that locate the rails have to be perpendicular to that so that all the parts are on their straight. Next is the profile tolerance. Each of those has to have a pretty exact profile because that's what the rails are going to be up against, and that's how those rails are located. Secondarily, those rails are located using pins. So with the use of those pins, they provide a more accurate location than the profile can. Next is the location of the dowel pin holes. It says 9 times dowel pin holes, where 6 of them are used to locate the parts as a tertiary datum, and then another 3 of them, 1, 2, 3, are used to locate the rails. The next here is the rail bolt holes. Those are just used to fix the rails in place. Notice on here that this drawing is only 2 views. There aren't cutaway views to show the depth of the pockets. The depth of the pockets wasn't critical in this design. They're all indicated with just notes here saying how deep they are. In hindsight, we should have added tolerances to those. Next datum on the list is the locating holes. So this is the datum for, this is the geometric tolerance for the holes that will be used to locate this and bolt it to the T-slots. The next one is the holes here for the Mighty Bite clamps. They're located with datums A, D, and C. And then finally are the clearance holes for the drilling operations on the parts. Those are located again with D, C, and A.
So DFM was a huge factor in designing this fixture, and the main way that DFM kind of came in is that we have a lot of pockets in which we're putting rails and other features, and you can't have tight corners on rails because we're not using any EDM processes. So if you look, for example, here's where a rail is going, and we have, I put turned corners everywhere, so we don't have any sharp corners. Everything is kind of has a fillet. So that was the main DFM constraint. Also, you can't make odd size holes or anything like that. We have to comply to what our cutting tools are able to cut out.
The result of the first round of milling resulted in several spots where they were only spot drilled. The text was misaligned. The opposite side of the text that was supposed to be selected was.
So when you engrave, you want to pick off on your cutter comp, so you go on the lines, so you kind of went around them.
As well as the dowel pin holes weren't drilled all the way through. Due to the errors in manufacturing, we decided to remachine our part. This is the redesigned fixture plate. You can see here, 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 and here, where the fixture plate has been faced off and re-engraved. Additionally, the two holes that were only spot drilled were drilled to depth and tapped, as well as all of the pins being drilled through. Physical inspection of the fixture plate determines it to be to the design spec. There are no obvious flaws, errors, or anything wrong with it looking at it. However, there were some flaws with the design. The depth of the plate and the height of the Uniforce clamps means that even though we only left the minimum amount of material at the bottom, the height of the clamps was too high to allow for the proper facing and contouring of the edge of any of the four parts that are clamped using this clamp. This design flaw was only discovered at the very end of the process as we were clamping and designing the tool paths to mill the different parts, so it was too late to do anything about it. The results, as you'll see in the next segment, show a part being thrown out of our fixture plate. The results of this project were mixed. Our fixture plate came out to spec, however, we found out at the end that there was a deeply flawed design. In the beginning of the project, we didn't think about the depth that we would need to mill these items to, and our instructor, shout out to Trian, told us that it would be totally okay to use the Uniforce clamps. This would have been the case had we had a deeper plate, however, we were restricted by that and unable to make our design work. We did wind up milling a couple of different halves of parts. However, one of them got thrown out of the machine when the non-Uniforce clamp let go. In conclusion, the objective of this project was to make a fixture plate for the IME 144 class. The plate was supposed to fixture 3 separate parts, 2 of each at a time, and run them through 2 separate processes. It was made to use It was made using Mighty Bite fixture clamps and a Mike 6 plate. The objective was to fit all 6 on a plate and make it easy to use and repairable if one of the dowel pins or clamps got milled into. The solution approach was to use a unique clamp, the Uniforce clamp, to minimize the amount of space that clamps take on the plate. This wound up being the downfall of the plate, as this was what prevented us from milling at full depth on 4 out of the 6 parts. If we were to redesign, I would do the same exact thing. However, I would do it right the first time so that we don't have to remachine various parts of it. And I would use a deeper plate and seat the Uniforce clamps deeper in order to make sure that they didn't interfere with the tool paths. This design was an ambitious design from the start, trying to fit all 6 of the parts on one fixture plate, as well as using a unique clamp from the rest of the class. It was a great learning experience and an understanding of all the different things that need to be taken into consideration when fixing a part, not just the location, not just the clamping, but also the tool paths and the way that the forces will work.